Hello, everyone. Okay, so let's move on now to the next topic here. Okay, so hydrogen. I just talked about. Remember, a hydrogen ion is just a proton. Um, so when an acid loses, well, I said when it loses just an electron from the hydrogen atom. So basically, it becomes positively charged, a hydrogen atom, or just a proton. So yeah, so that's what that statement it means. So basically, when you lose the hydrogen atom, it becomes positively charged with just a proton. So that's why we say a hydrogen ion or just a proton. So usually I just say proton. So I may say that a lot. So what I mean by that is a H plus ion. Okay. So when we identify a Brønsted-Lowry base, it's a little more difficult than a Brønsted-Lowry acid. So the key is to identify which molecule has an atom with a lone pair of electrons. So in this reaction, for example, ammonia will donate its pair of electrons to water to form ammonium ion and hydroxide ion from the water molecule. So here are some examples of atoms with lone pairs, and they are Brønsted-Lowry bases. So ammonia, water, and then here's carbonate ion. So those can act as Brønsted-Lowry bases because they have an atom that has a lone pair of electrons. So some examples that do not fit this rule, they don't have any lone pairs. So these are not Brønsted-Lowry bases because there are no lone pairs on any of these atoms. Methane, hydrogen, and then ammonia. So those cannot act as bases because they have no lone pairs to accept a proton from an acid. Okay, so let's identify which ones, which reactants is the Brønsted-Lowry acid and which one is the base in the following reaction. So if we look at reaction A, we see here that fluorine, or HF, is donating its hydrogen in this reaction. So we say the acid is HF. So acid, hydrofluoric acid, HF, okay? And then if we look at the base, the other molecule must be the base, right? So hydroxide has a negative charge, so it has a lone pair that can accept a proton. So if we compare OH now to H2O, even though they're in different places, they are related by a proton, so the base now is going to be OH minus. So in this case, when I ask questions like this, we are going to look in the forward direction. So the forward direction, okay? So always look in the forward direction. But if I do put these arrows here, I will tell you, I'll be in the forward direction. So going from left to right is the forward direction. The reverse direction is from right to left, okay? So usually in these questions, I'll be like, okay, this reaction doesn't really go to completion because the acid is not very strong, so it doesn't dissociate all the way. So I'll tell you, say, okay, based on the forward direction, or I'll say based on the direction to the products of the forward reaction, what species is my acid and which species is my base? I'll ask something like that. Okay, so it won't be. I'll be very clear on what I expect. Okay. So they're all pretty much equilibrium reactions here. Okay, so for B, if we look at this molecule here, acetic acid, and then we look at the molecule on the right-hand side, we see it's lost the proton now. So the acid is going to be my molecule on the right, CH3, CO2H. And then the base is going to be the other compound, because if we look at water, it's now accepting a proton to becoming H3O+. So that's our base. So base, molecule that has accepted a proton. Acid, molecule that has donated a proton when you compare the two structures on the reactant and product side. All right, C here, it's a little bit tricky, I think. So here's one compound. Now let's look for this compound on the right side. Oh, and we see something pretty similar here. C6H5NH3 plus. So it has gained a proton. So our acid now is not this compound. It's going to be the other one. So if we look at nitric acid here, and we see compare the similar looking formula on the right, we see we have NO3 minus, so it has lost a proton. So our acid is HNO3. So you can't just memorize where the location of these molecules are in the reaction. There's no really rule for how we ordered them. So you can't rely on memorizing the placement in the acid-base reaction. So just look at the molecule that's losing a proton, going from left to right. That's going to be your acid. And then your base is the compound that gains a proton from left to right. In this case, it's going to be aniline or aminobenzene, or aminobenzene, or what we call it, like phenylamine. So this is going to be C6H5 and H2. Okay. So let's talk a little bit more about acids and bases. So acids can be uncharged molecules, like we've seen here. The uncharged molecule is HCl. It can also be positive ions. NH4 can also donate an electron to produce ammonia and water again when it reacts with hydroxide. Actually, ammonium hydroxide in solution, it's in equilibrium, so they can react to give you solvated ammonia in solution. And it can also be negative ions as well. So for example, if I have what we call a polyprotic acid, that means it has multiple hydrogen atoms that can be donated sequentially. So even negatively charged molecules can be acids. So there's a lot of possibilities here. Okay. So if we only have one acidic hydrogen atom, like HCl, we call it a monoprotic acid. And now if an acid has more than one proton, we call that a polyprotic acid. And it can donate more than one hydrogen ion in solution based on the reaction conditions. For example, the first step of sulfuric acid is very far to the right. So it goes to completion. So the first step is very favorable to products. So it'll form the products right away in solution. However, if you were to think about the solution, you can, if you just have water, you can't get 2 equivalents of hydrogen ion in solution because the second step is weak. I won't say weak, but the second step is slow, and it doesn't go to completion. So to go to completion, it'll need some help with like a strong base. But if you just have water, the second step doesn't go to completion, and you see those 2 arrows. That signifies that the reaction is in equilibrium with all 4 species here being present in solution. So a big part of chemistry also is equilibrium kind of reactions. That's how pretty much buffers work in our body. So like phosphate buffers in biological systems. In our body, we have buffers to mediate, mediate big changes in pH, especially if you eat something very acidic like kimchi or something really. I don't know if things are basic, but like maybe high pH water, I guess. I don't know. Usually the foods I eat are like sour, kind of spicy, so it kind of indicates that. It's probably something acidic, especially if it's sour. Pretty much an acidic, probably acidic molecule there. But some basic things you probably eat, they're probably used for flavoring, so you don't notice the basicity at all. But it does affect the flavor. But it's hard. It's kind of harder to spot. But like if you eat bitter stuff, that's probably has it's probably a good portion of it has something basic to make the thing bitter. But like if you were I don't know if a lot of people eat this, but like bitter melon, I eat a lot of bitter melon, so it's a very bitter food, but it's supposed to be good for you. So I eat it just because I want some some nice balanced meals with some vegetables. So try to keep my diet a little bit balanced here. Okay, so that's how pH can be modulated there. These equilibrium reactions, they help modulate pH levels in the body and keep your body at homeostasis. So it's not really going to shock if you eat too much acid, foods with too much low pH values, or something that's maybe a little more bitter, high pH values, etc. Okay. So one thing I want to stress, but I'm not going to necessarily emphasize on the test, is conjugate acid-base pairs, because this tends to confuse students. But you'll learn more about this acid-base chemistry, a lot more, in more great detail in Chem 401. So we're just going to touch the base here. Just touch, our basics here for what we'll be doing in lab. So conjugate acid-base pairs. So in an acid-base reaction, we will have what we call conjugate acid-base pairs. So a conjugate is basically a species that's related to another species in solution by a single proton. So conjugate has many meanings, but in chemistry, it usually refers to an acid or base pair that's related by the loss of a proton, or the loss or gain of a proton. Okay, so for HCl, if we compare them here, we see this is the acid. So if it's default an acid, then the base here is what we refer to as the conjugate base. Okay? And then when we have something acting as a base right here, the water and the H3O plus, this will be the conjugate acid. So they are related to each other by the addition of a proton. So if originally it was a base, becomes it gains a proton, the result is the conjugate acids formed. And then once you're an acid and you have lost a proton and you become a negative ion, that will be the conjugate base. Okay, so in this case, HCl is the acid, Cl minus is the conjugate base, water is the base, H3O plus is the conjugate acid. So in this case, you'll always have a acid, conjugate acid, and base acid, conjugate base, and then a base, conjugate acid pair. Okay, so there'll always be pairs like that. Two conjugate pairs. Conjugate acid, then conjugate base. One will be from the acid, and one will be from the base. Okay. Now, let's do another exercise here. Write the chemical equation for the reaction of porous acid, so HClO2, with potassium hydroxide. We're going to identify the acid and base among the reactants, and then the conjugate acid-base pair that's formed in this reaction. Okay, so hydrochloric acid is HClO2 plus KOH, which is a base. And this will react to give us water. Remember, so we have a strong base here. So a strong base and a weak acid. So typically they will react to be a neutralization reaction. So I would never give you a, well, I won't say never, but usually in this case we have a strong acid and a weak acid, a strong base and a weak acid reacting. Or the converse of that, a weak base and a strong acid reacting. They'll always give us a neutralization reaction here. And then our other compound, remember, it's a double replacement. So this is combining with hydroxide, and then the chloride ion is combining with potassium, so we get KClO2. So we can actually, so since hypochlorous acid is a weak acid, we can write it as HClO2. And since potassium hydroxide is a strong base, we could write it as 2 ions here. And then water does not dissociate, so we keep it the same. Then we get plus. Potassium chloride is chlorite is a very soluble salt, so we get K plus ClO2 minus. And then here we can cancel out the like terms on both sides, so we cancel out potassium, and we have HClO2 reacting with hydroxide to give us water and the chlorite ion. So we see here now it looks more clear what is the conjugate base and the conjugate acid. So let's look at these two terms. So HClO2, if we look at both sides of the equation, they're related by a single hydrogen being lost as we go forward in the reaction. So this is going to be our acid, and therefore ClO2 is our conjugate base. Because now we have lost a proton, we become a conjugate base. And here hydroxide is our base, because if we compare both sides of the equation, it becomes water, which gains an additional proton. It has now an additional proton, so this is the conjugate acid. Okay? So conjugate acid, you gain a proton from a base, and then conjugate base, you lose a proton from the acid. So that's a conjugate acid-base pair. Okay. Now let's move on to what makes a strong acid. Let's go over some terms here. Strong acid and bases to remember. All right. Okay. So we'll go over a few of these here, then we'll pick it up in the next video. So, strong acids. Acids that dissociate or ionize completely to the ions, so none of the acid molecules are present when it dissolves in water. Okay, so these are the 7 strongest acids we know, or that are commonly, introduced in Gen Chem. So the hydrogen halides, HCl, HBr, HI. HF is an exception. It's a weak acid. And that has to do with the fact that fluorine is a very, very reactive ion. So it doesn't like to leave and form ions in solution because it's just so reactive. And then there's oxo acids, nitric acid, sulfuric acid, and then HClO3 is chloric acid, and then HClO4 is perchloric acid. So these are all good acids, and they're also very good oxidizing agents. So when you have acids of these types, they tend to be oxidizing agents as well, oxo acids. So that's one thing to keep in mind too. If something's a strong acid, it's very reactive, so it also tends to react not only in acid-base reactions, but also oxidizing redox reactions as well. Okay, weak acids. They're acids that partially dissociate or ionize to ions. So they're acids that have these equilibrium arrows here. So for the second example here, right here, that's a weak acid. HSO4 minus is a weak acid. And if we go up here to phosphate, hydrogen phosphate, that's a weak acid. NH4 plus, also weak acid. So when we have these double-headed arrows, double directional arrows here, that indicates that the acid or base is weak and doesn't completely dissociate to ions. When there's only a single arrow, like in this example, we see that everything completely reacts to go to completely ions in solution. And that's what a strong acid or base does. So some weak acids are H2S, hydrosulfuric acid in solution, HF, hydrofluoric acid, HCN, hydrocyanic acid, and then HClO2, which is chlorous acid. So those are weak acids. They partially dissociate. All right, strong bases are just like strong acids. They dissociate completely to form metal ions and hydroxide ion in solution. So The hydroxides, lithium, sodium, potassium, rubidium, and cesium. And then group 2 hydroxides, strontium, calcium, and barium. So magnesium is not included in this list because it has very poor solubility in aqueous solution, so it's normally not included in the list. But these are the strongest hydroxides. But for the ones you use as strong bases, usually you only see sodium and potassium. We usually don't use rubidium, cesium because they're way too reactive and they're costly to make. And lithium can act as a strong base, but it's weaker than sodium and potassium. So sodium and potassium are pretty much the golden standards here that we see and use, and they're very cheap. Lithium is actually, I think, more expensive than sodium. Okay. Weak bases are the same, are kind of the same thing in relation to weak acids, but most of the time, the weak bases we see are nitrogen compounds, so amines that are similar to ammonia. So organic analogs of ammonia, which is inorganic, are amines. So like, if you ever cook fish and fish smells, right? That's because amines are present in there, and they're very smelly. So usually nitrogen smelling compounds are really associated with very bad, unpleasant smells. So if you ever wondered what causes the smell of, like, when you go drop a number 2, it's because of a nitrogen compound. It's actually not because of like sulfur, like proteins, they have sulfur in it, or phosphorus. It's not because of that. It's because of a nitrogen bearing compound. So nitrogen is the cause of all our foul smells. Okay, so right, so nitrogen is very peculiar. Well, I wouldn't say peculiar, but it's very basic. So anything with nitrogen in it is pretty much a weak base. Okay. But it all depends, right? So neutral nitrogen atoms, they're weak bases, like ammonia. All right. Ionic compounds that also contain are derived from weak acids are also weak bases. For example, sodium sulfide in this case. So the sulfide, it comes from H2S, right? So the conjugate bases there are typically weak bases as well. Okay, so for example, H2S. And I'll go over more the weak bases in these tables in the next video. So I'll see you then.